All right, grade 12s, this is the next geometry theorem. It's quite a big theorem. It's quite easy though. It's really nice to work with. So when we're working with it, we're going to be working with similarity. So it says here that the corresponding sides of two equiangular triangles are in the same proportion, and therefore the triangles are similar. So if we have two equiangular triangles, then we are looking at similar proportions, and we are looking then at similar triangles. Okay, so we have the same proportion, similar triangles, because we have two equiangular triangles. So that's what we're going to be working with here. So in this case, you do need to know the proof. So you'd be given two triangles. Here they are. They are not identical, but they are going to be similar. But we've got to prove that. And the way we work with similarity is angle, angle, angle is the most common one. So we have angle A equal to angle D, given. Angle B equal to angle E, given. Angle C equal to angle F, given. And so now the tricky bit is to prove that that this ratio exists for all combinations of the sides. So AB to DE, AC to DF, BC to EF, all in the same proportion. All right. So the first thing we're going to do is construct. So these are your two constructions. You're going to construct point G and point H in such a way that it makes AG and DE equal and AH and DF equal. And then you're going to join GH. So it's almost like you're trying to make another little triangle using construction. But the one thing that you've got to be careful of, they have not told you that GH is equal to EF. All right, so when you construct, you can't make GH equal to EF. So then we're going to work with the two smaller triangles now. So we're going to work with congruency for them. So in triangle AGH and DEF, we have AG, the purple, equal to DE, the purple, by construction. All right, you constructed it. Then angle A is equal to angle D, given. And then the blue construction, AH, is equal to DF, constructed. So our two little triangles are equal because of side, angle, side. They are congruent. All right. The fact that GH then is equal to EF is irrelevant. We're not interested in that. What we are interested in is that now G1 must be equal to angle E. So I can put a little circle there. All right. And angle F is equal to angle H. All right. But then we notice something in this triangle now, that these two are equal to each other and these two are now equal to each other, which means we have an upside down F. We have corresponding angles from either side. You could do it from this side, so we have the F looking like that, where we have our corresponding angles are equal, which means that these two lines are parallel to each other. If those two lines are parallel, then we know, if those two lines are then parallel, we can assume, not assume, but we've proved in the past that these sides are then in proportion. So we know that AG was constructed and so was AH. So we've got to make sure we get rid of those ones. And so if we look here, so we know that AB, so in this case we're going to work with AB, big side, to AG, top bit, is equal in ratio to AC to AH. And the reason that they have not put in here, so you have to put it in, is that there is a line parallel to one side of triangle. That's theorem 1. And we've just proved that the lines were parallel. But remember, we don't want AG and AH in our final answer because that wasn't in the question. The question doesn't have AGs and AHs. So we've got to link the fact that we said that AG, so where we see an AG, we can replace it with a DE, and where we see an AH, we made it equal to DF. And then that's exactly what they wanted us to prove. They wanted us to prove that ratio there, AB to DE, AC to DF. Then we do something called similarly, meaning you don't have to redo the whole proof because that's ridiculously long. You could prove in a different perspective. So you could have done the construction in this way, and then you would have proved then that AB and DE is BC to EF. And then that would have made all of them equal to each other. So when you have the similarity situation here, which we've gotten to, okay, all the triangles are going to be similar to each other. Why? Because we end up with the same ratio of sides, the same proportion. So the proportionality theorem is used. Theorem 1 is used to prove theorem 3. And this is that now we have these sides that are in proportion to each other. And then you'll see on the note that you get in class that the reason that you'd work with is similar triangles or equiangular triangles. All right, the best way that I know how to work with this is just to do an example. So it says here in triangle PST, the big triangle, TS is perpendicular to PS and RQ is perpendicular to PT, which have been shown here. Question A says, prove that triangle PQR is similar to triangle PST. So before you even work with this, I want you to draw out the two triangles as they are. So PRQ and with the correct angle that is there. So that's R1 and Q2 is trapped there. So there's the one. And then PST is the big one. S has got 1 and 2, and then the whole of P. Now, we've already been told that is 90 degrees. R1 is also going to be 90 because both sides are going to be perpendicular. Okay, you can't just have one side, one piece perpendicular. And so then you just have to match the equal angles. So let's see. P is common. We've got two 90-degree angles. And then, honestly, that's it. We've done it. So let me show you what I mean. So the first angle, so first thing in triangle PRQ and triangle PST, we have angle P. So the first angle, angle P equals angle P, common. Then our second pair that is equal, angle R1, the 90 degrees is equal to S1 plus S2, given, equal to 90 degrees. And then what's beautiful within triangles is that once you have two sets of equal angles, the third one has to be by angles of a triangle. So please just match up these Q2, R1 and P go together, and then PS, and then so I'm going to match up T. Angles of a triangle. And just to clarify for those who are not sure, let's pretend that angle P was 20. So we've got 90 and 20. This must be then 70. We've got 20 and 90 here, that must be 70. They have to be equal to each other. Alright, so we're going to then say, therefore, triangle. And now what I want you to do is take the order that you proved it similar in. PRQ is then similar to triangle PST. Alright. And your reason? Angle, angle, angle. Or a nicer way, equiangular. Nice word, equiangular. They are equal in angles. Then what I want you to do, to find which sides then are matching, which ones are going to be in the same proportion to each other, we are going to do little loops, and you've got to use colors for this. Okay, so we are going to work with 3 colors. Kind of looks like a little smiley face. You can even put in little eyes if you want. Like a little frog. Okay, so when you're working with these, I call them the loopies, do them in different colors. And then the colors from the 2 triangles are the matching corresponding sides. So just like we proved in the previous one with the ratios, it means that PR to PS, RQ to ST, PQ to PT are all in the same ratio. So let's see what they're asking us for B. They're asking us now to say that RQ to PQ is equal to ST to PT. So that's the question. Now all you need is your loops. So that's what we expected to do. So now we've got to see. RQ is a purple loop, right? Now remember, ratio means divide. So I'm going to divide by a PQ. PQ is a yellow. And that's going to be equal to now ST over PT. Because that's what that's ratio means, divide. Now can you see that we have 2 colors and 2 of each? And the reason I'm allowed to use here is similar triangles or equiangular triangles. So now you can say, therefore, RQ to the ratio of PQ equals ST to PT. That's it. As long as you have the correct amount of loop colors, so 2 of each color, make sure you don't use the same one from the same triangle. You've got to have 2 colors from 2 different triangles and then match them up. Okay, the more we do, hopefully it will become a bit clearer. Okay, so then example C, they're saying to us, PR dot, not colon, dot PT is equal to PQ dot PS, which means instead of dividing, we're multiplying. So you've got to understand that what they've done is, imagine we did this in the previous question, it's like cross-multiplying these fractions. So we've got to undo them. Right, so the idea is here is to start with, let's say, PR is green. Right, we know in order to cross-multiply, we have to have PT on the bottom of a fraction. So PT in the other triangle is yellow. Okay. Then on the other side we have PQ. PQ is yellow and PS is green. Right, and why have I done this? I've got 2 greens, 2 yellows from different triangles each set, and now I can cross multiply. How do I know I'm allowed to just stick these fractions together? It's because the color scheme matches my loops, and we are getting 2 colors from 2 different triangles, 2 pairs. Okay, and the reason is then similar triangles or equiangular triangles. When I cross multiply, I get PR times PT equals PQ times PS. So that is the required to prove. You don't even have to put that there. You go straight into the answer. And then that's it. The next example that you can find in your PDF is example 9. It says A, B, C, and D are concyclic points, meaning they each lie on the circumference of the circle. A circle surrounds them. DOC and AOB are chords, and that means that you can't assume that O is the center of the circle here. They didn't say they are diameters, they're chords. DB and AC are joined. Prove that, and then they give you AOC must be similar to DOB. So before we even start going into similarity, for similarity we need to have two pairs of angles equal. In this case we could do 3 pairs of angles. It would work, but remember you only need 2 pairs. So let's see, O1 and O2 are vertically opposite to each other. Then D and A are the tips of the butterfly, as well as B and C, so they are angles in same segment. Now that we have our triangle angles, now we can actually write the proof out. Okay, so we know we have to state what triangles we're working in. In triangle AOC and triangle DOB. Okay, so because I've mentioned the AOC triangle first, I'm going to go with that first. So angle A is equal to angle D, and that is angles in same segment. Angle O2 is in that AOC triangle is equal to angle O1. O1. And that's vertically opposite angles. And then you could use angle C is equal to angle B because of also angles in same segment, which for some reason mine have gone all over the place. So let's just fix them. So we would have that one and that one, that one and that one, that one and that one. Okay, so you can either do angles in same segment, or you can just say angles of triangle. Okay, all angles in same segment. But you don't need to do both, just pick one. So then I have proved, in the order I've proved it, that triangle AOC is similar to triangle DOB. All right, remember, we don't put it in alphabetical order. We make sure we put it in the order we've proved it. Okay, so if you did it as OCA, then you'd have OCA, you'd have OBD as your triangle. All right. So the reason for this is either angle, 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 or you talk about equiangular. Right, they have 3 pairs of equal angles, and then from this point we do our loops. All right, so our loops, I've matched the first 2 letters, the second 2 letters, and then first and last letter. And so then for question B, they are asking us to prove, so our required to prove is that OB over OD is equal to OC over OA. All right, so now all we've got to do is use our loops, and if we end up with 2 of the same colors, 2 pairs of them, then that's it. That's all we have to do. So let's find. We need OB. OB is yellow here. So OB is yellow. We need OD. OD is blue. Now let's see if we get yellow and blue on the other side. We need OC over OA. Yes, it works. So we've got yellow and yellow, blue and blue. And the reason we're allowed to just randomly use this is because we have similar triangles. We proved that triangle AOC is similar to triangle DOB, and using the theorem proof It says if we have similar triangles, it means their sides are in the same their corresponding sides, should I say, are in the same proportion. So that's why we use the loops. So blue to blue, yellow to yellow, pink to pink, they work out. All right, that's it. We're keeping it very simple for these first two examples and for the exercise 4. So on the Google Classroom, there is an exercise PDF and there will be a memo as well. You need to follow the exercise 4 from Google Classroom. The one in your textbook is different. This is using another textbook. And so the one in your textbook, you're welcome to do the exercises, but that will not match the memo. Okay, you'll have to use the back of the book to test yourself, or request when we get back to have a look at the memos for those exercises. All right, so please use the ones on Google Classroom. The next video will cover the slightly harder examples and another exercise, and then the third exercise will come, and then that will be it for the geometry.